Today we will talk about random variables. Suppose we have an experiment with the sample space script S. Our interest in the experiment might be related to a particular property of an outcome of the experiment as opposed to being interested in the outcome itself. Uh, let's work out a few examples to get a sense for what this means. So suppose we toss a two-sided coin 5 times. The sample space for this experiment is of size 32 and it has elements of the form HH all the way up to TTTT. Then, given an outcome omega inside the sample space, we might be interested in questions like what is the number of heads in the outcome? Or we might want to ask, are there at least two heads in the outcome? Is the number of heads equal to the number of tails in a given outcome? Or are there more heads than tails in the outcome? Another experiment could be rolling two die. The sample space for this experiment is pairs of numbers x comma y, where both x and y range from 1 through 6. The sample space is listed out here and it is of size 36. Then, for any outcome inside this sample space, we might be interested in questions of the form, is the sum greater than 5? Or is there at least one even number in the pair of numbers that we have chosen? Is the sum divisible by 3? Or is the max of the two numbers greater than 4? A third experiment could be working with a bag that contains 5 red balls and 8 blue balls. And the experiment consists of drawing 3 balls from the bag. Sample space is listed as here. And given an outcome, we might be interested in counting the number of red balls in the outcome. Or we might ask the question, are the number of red balls more than the number of blue balls? To make this idea precise, let S be the sample space of an experiment. We will define the random variable x as a function whose domain is the sample space S and range is a new sample space, typically a subset of R or sometimes all of R. That is, x is going to be a function going from S to R, sending an outcome omega in S to x of omega. The image of the random variable x, that is x of S, is going to be the set of all values of x on the outcomes in S. X of S then specifies a new sample space for the original experiment in the context of a certain property of interest that we're going to use to define the random variable x in the first place. Now, suppose C belongs to XS, that is, it is a value of x, then we can construct the set x equals C. This is going to be the set of all outcomes in the sample space that are mapped to the point C under the random variable x. We note an important fact, that is, if script x, a subset of R, is the set of values of the random variable x, then the sample space S is going to be the union over C belonging in script x of the sets x equals C. And this is going to be a disjoint union, which means that the subsets x equals C will form a partition of the original sample space S. We next work an example. Suppose we toss a coin 4 times independently. this is a two-sided coin, then the sample space of this experiment is calculated as follows, and we can consider the random variable x that is going to count the number of heads in an outcome. For example, x evaluated on the outcome HHHT is going to result in 3, and x evaluated on HTHT will be the same as x evaluated on THTH, and it's going to equal 2. Now, if script x is the set of values for x, we note that script x is going to be 0, 1, 2, 3, and 4. And we now calculate the sets x equals c for c inside script x. So x equals 0 is calculated as the set when there are 0 heads. This is going to be t, 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 t. And the rest of the x equals c's are calculated as follows. For example, when x equals 2, we notice that there are 6 elements inside the set. And when x equals 1 and x equals 3, each of those sets have 4 elements. And x equals 0 and x equals 4 have 1 element each. Observe that the union over the values of x is the entire sample space. Furthermore, we can define the probabilities of the event x equals c as follows. We just take the sum of all the probabilities of the outcomes inside the set x equals c. Remember that this will require us to have the probability distribution for the original sample space S. We apply this strategy to our example to get the probability of x equals 1, which will be the sum of the outcomes HTTT, THTT, TTHT, and TTTH. If we assume that all the outcomes in S are equally likely, then we can notice that each of these probabilities will be equal, and they will equal to the number 1 over the size of the sample space, which is 16 in this case. So therefore, the probability of the event x equals 1 is going to be 4 times 1 over 16. We can similarly calculate the probability of x equals 0 to be 1 over 16, the probability of x equals 2 to be 6 over 16, the probability of x equals 3 to be 4 over 16, and the probability of x equals 4 to be 1 over 16. We can organize this information into a table where the first row corresponds to the values of x and the second row corresponds to the probabilities of x equals small x. Such a table is called the probability distribution table for x, and we will define these in very general settings in subsequent videos. We finish up by showing a calculation of the sum of the probabilities corresponding to the events x equals c. And recall that these events were a partition for the sample space, so the sum of these probabilities has to rightfully equal 1. This completes a very brief introduction to random variables. We will be using these extensively in what follows in this course. This is all for now. You take care of yourselves, and I will see you around.